Let's talk about angular acceleration now. So this is when there's a change in angular velocity. And of course, we just want to know what's the rate of change in that angular velocity. Of course, angular velocity being how much an angle is changing per unit time when something's going in a circle. So we we calculate that much the same we did with regular acceleration, right? Linear acceleration is a change in speed over time. This is the change in angular speed over time. And that's how we can get our angular acceleration, where we use an alpha for angular acceleration, okay? So of course this is our average. Always make sure that it is change in the angular velocity over change in time. So again, if we have angular velocity of 0 and then it goes to, 5, then we can just use 5. But then if you're going from 2 to 5, then that's a change of 3, okay? So just like with linear acceleration, we have the same rules if something's speeding up or slowing down. So if we have the same sign on something, so if the angular acceleration and the angular velocity are in the same direction, so either both positive or both negative. So of course, when they're both going counterclockwise, they're both positive or greater than 0. Both going clockwise, they're both negative, less than 0. But that's, of course, when it is speeding up. Okay, so same sign, speeding up. And that's just like when we have linear velocity and acceleration. Okay, and then when we have two things with opposite signs, so say our angular acceleration is positive, but our angular velocity is negative, that's of course when it's slowing down. So that's something like it's moving this way, but it's slowing down and eventually going to stop, okay? Or in this case, when the angular velocity is positive, but the acceleration is negative, again, that would be slowing down. So it's moving this way, but it's still slowing down, okay? So opposite signs always mean it's slowing down. Okay, and that's how angular acceleration works. Except for, unfortunately, it's not actually that simple. So that is angular acceleration. So I shouldn't say that. Angular acceleration is that simple. But then when we think about total acceleration of something that is traveling in a circle. Okay, so there's two things we really have to look at when we're looking at the entire total acceleration. Okay? Because there's still acceleration happening now in two linear directions, and that's our tangential acceleration and our centripetal acceleration. So when we went over centripetal acceleration, centripetal motion, we were assuming that the thing going in a circle was going in at a constant speed, right? That it wasn't speeding up or slowing down. But now, if something is speeding up or slowing down, then it has a tangential acceleration, right? It's a speeding up or slowing down in this direction. If this is actually already moving in that counterclockwise direction, this actually is showing us something that is speeding up. And then, of course, we know we have our centripetal acceleration or rotational acceleration in this case, and that's always going towards the center of the circle. So this is the centripetal acceleration is the one that is telling us that it is constantly changing direction, but the tangential acceleration is the one that's saying it's speeding up as it goes along or it's slowing down. Okay, and so we can calculate these linear accelerations, the tangential one and the rotational acceleration. Well, we already know how to do that. So our first thing here is our tangential acceleration. What we do is we take r, the radius, and multiply that by our angular acceleration. And then, of course, for centripetal acceleration, we already knew this. We already knew centripetal acceleration. Here it has an r next to it. That's the same as centripetal acceleration. Was v squared over r. We got some stuff taken out of there. But v is equal to r times omega. And so we're going to square that, put that over r. And then that should equal to r times omega squared, right? Because it'll be r squared times omega squared divided by r. The r's will cancel out, and we get r times omega squared. So there we go. We have our two sort of equations for two different types of acceleration that are going on. Again, we didn't have this. We had a tangential acceleration, except for it was 0 when we went over centripetal motion, because we were only looking at things that were going around in a circle at a constant rate. So this is still holds true to that, but now I'm saying, what if you speed this up or slow this down? Then we know that there's going to be another acceleration. Okay? So again, this is still looking at total acceleration, not angular acceleration. This is completely different than angular acceleration, because that's, of course, the rate at which the angular velocity is changing. And so I'm actually just talking about what is the linear acceleration of something at point P that's moving in a circle and speeding up or slowing down. So how we would do this is we would find our vector addition triangle here. Okay, so we know that if we look at our tangential accelerations kind of going up at that direction here, and our rotational acceleration, same as centripetal, I'm going to move its position so it's more like that. And then our total acceleration then looks something like that. Okay, so this is a right angle triangle because these two guys are at perpendicular to each other, because of course this guy's going, our rotational acceleration is going towards the center of the circle. Our tangential acceleration is tangent, which then by definition it must be at a 90-degree angle to the radius. So therefore we can just use Pythagoras to find our total acceleration, because it is just the vector sum of those two accelerations. So our total acceleration will just be tangential acceleration squared plus rotational acceleration squared, all square rooted. Of course, we have our alpha for our tangential acceleration. We have our omega squared for our rotational acceleration. If we look at that, we have r squared, 8 alpha squared plus r squared omega to the power of 4. Just so you know, if you don't know how they're skipping from this step right here to this step right here, well, if you think about that, that's the same as r squared times alpha squared plus omega to the power of 4, square root all that. And then, of course, you can just bring that up, but over into its two separate square roots. And then, of course, the square root of r squared is just r. And so that's how we get this final equation right here. Okay. That's that. How does that sound? Sound good? So remember, that is total acceleration of something that is moving in a circle, but is speeding up or slowing down. It is different than your angular acceleration, which is the rate at which your angular velocity is changing. This is its actual total acceleration of the object that's moving in a circle. Okay, taking the fact that it's speeding up and slowing down or slowing down into account, and also taking into account the fact that it is constantly changing its direction. Okay, so now that we know a little bit more about acceleration of something that is moving in a circle, let's do some examples. Okay, so we have a discus thrower turning with an angular acceleration, so it's really important to note that it's the angular acceleration of alpha is equal to 50 radians per second squared, moving the discus in a circle with a radius of 0.80 meters. Great radius, angular acceleration, that's what we got. So we model the thrower's arm as a rigid body, so r is constant, always good. Find the tangential and centripetal components of its acceleration at the instant when the angular velocity is 10 radians per second. Okay, so first we want the tangential acceleration. How do we find that? R times alpha. Great. We got both of those, so that actually makes our life really easy. So 0.80 meters times 50 radians per second squared. We multiply those together, we get 40 meters per second squared. Okay, the radians really only matter when you want them to matter. They don't really need to cancel out. Don't try to understand it, just go with it. And then we want the rotational or the centripetal acceleration, which of course is v squared over r, but we are going to use this other equation for it, r times omega squared, r being radius and omega being the angular velocity. And of course we did want to find it at the instant when it's going 10 radians per second. Okay, so that centripetal velocity will be different. That centripetal acceleration will be different depending on how fast it's going. So usually we want the velocity right as it would leave this person's hand or something like that. Okay, so there we go. That's our radius. And then of course our rotational velocity is 10 radians per second, which of course that is a total of 80 meters per second squared. Okay, so they're not always the same. Actually, they're pretty much never the same. So there you go. That's that. That's how we're going to calculate those things. Now, finally, one more thing I wanted to get into with acceleration. Now that we know there's such a thing as angular acceleration, we'll think about all the equations we have for just regular linear acceleration, right? We had all these equations here that we could use when we had linear acceleration. Okay? And this is, of course, when acceleration is a constant, which is the only thing that will ever go over at a 20, a grade 11, or even any high school level of physics. Okay? So I know these equations look a little bit different to you, but this one is basically just a rearrangement of acceleration is equal to change in velocity over time. Then the next one, they're saying, like, say your original displacement was different and wasn't 0, but this one's basically the same as displacement is equal to final velocity plus initial velocity over 2 times time. Okay, this third one is basically the same as displacement is equal to initial velocity times time plus 1/2 times acceleration times time squared. And the fourth one is VF squared equals VI squared plus 2AD. So again, they're just saying, what if your initial distance was not 0? So they're saying change in distance, which is displacement. So yeah, those are basically it. But since we now have all these angular kind of analogs to all these linear things, instead of displacement, we have, what do we have? Instead of displacement, we have angular displacement, which is, of course, theta. And instead of velocity, we have angular velocity, which is omega. And instead of A for acceleration, we have alpha for angular acceleration. So therefore, we can take all these equations and replace theta for displacement, omega for velocity, and alpha for acceleration, and we have all the same equations except for rotational motion, which is really, really helpful. So again, these are kind of those analogs, but if we want to put this in terms of things that we know, again, this first one is really just alpha is equal to final angular velocity minus initial angular velocity divided by time. Of course, time is the one that's constant throughout. Okay, the second one is theta is equal to omega f plus omega I divided by 2 times t. And so you can use any of these equations you want. This guy is theta is equal to omega I times t plus 1/2 alpha t squared. And of course, the final one is final omega squared equals initial omega squared plus 2 times alpha times not d, oh my goodness, times angular displacement, which is theta. Okay, so I'm just taking all my equations for acceleration that we've dealt with, and I'm substituting in angular displacement, angular velocity, and angular acceleration. And so then when we do other questions, we can always just use these equations that we already have, but then substitute in their angular analogs. So let's do a few examples like that. First of all, just want to make sure, did you get down what's happening when something is slowing down? It's the exact same thing as what we covered in kinematics. So this is telling you which direction the fan is going. So that's the direction the fan is moving. But somebody just turned it off and now it's slowing down. So which option describes omega and alpha? Omega being the angular velocity. So if we look at the angular velocity, it is going clockwise. Okay, so that's the first thing we want to know. And omega is going clockwise, which means it should be negative. All right, so we already know A and B are both out because they have omega as positive, which we know is not true. Okay, so we know it must be C or D where omega is less than 0 and it's slowing down. So that means that omega and alpha should have opposite signs. As it's slowing down. So therefore, if omega is negative, alpha should be positive. So our answer should be C, because it's the one where it has omega as negative and alpha as positive or greater than 0. And there we go. Okay, let's do another example. A bicycle wheel is being tested at a repair shop. The omega, the angular velocity of the wheel, is 4 radians per second at time 0. And its angular acceleration is constant and equal to negative 1.2 radians per second squared. Okay, we got some good stuff here. A spoke OP, so that's from this point right here. O, here's P, so this spoke right there coincides with the positive x-axis at time equals 0. That's really important because remember, we always want angular displacement in reference to this positive x-axis arm, right? So angular displacement should always be in terms of that. So that's actually really, really good that we have that, okay? So that's time t equals 0 is when we're at the positive x-axis, because then we can go ahead and just find the angular displacement, and we don't have to like subtract a different displacement from that. Okay, so let's figure out what we're figuring out. What is the wheel's angular velocity at t equals 3 seconds? Okay, so again, I'm just going to use sort of my analogs from the kinematics unit and say, okay, what do I have? I have the initial angular velocity. I have angular acceleration. And I have time, and I'm looking for final angular velocity. So if I go back to all these equations, I say, what can I use? And I think we should just use our handy dandy, like run-of-the-mill, the first one that we go to when we're dealing with acceleration, and that is change of velocity over time, because it looks like I kind of have everything else that I need from there. Okay, so that's alpha is equal to omega f minus omega I divided by time. And then we're looking for the final angular velocity. Okay, so we rearrange there. And we should get that equation, and then I can just plug in the numbers. I'm going to go beside this or else I'm going to run out of room. Okay. So again, don't forget that negative. So that means it's the acceleration must be going clockwise, which means it's slowing down because our initial velocity was positive. Okay, so of course we know the change in time is 3 seconds. And I'm going to add to that its initial angular velocity, 4 radians per second. Okay, and when I calculate that, I should get 0. Where was it? 400 radians per second. Okay. So it's still positive, but it is lower than the initial velocity, which makes total sense because, again, that initial velocity and the acceleration are in opposite directions. So therefore, we know this guy is slowing down. B, what angle does the spoke OP make with the positive x-axis at this time? So I'm guessing at the 3 seconds. So basically, I want the angular displacement at this time. So again, I have, well, I do have final velocity, but I have initial velocity, I have alpha, I have t. So what are we going to use? Well, basically, we kind of have our pick at this point, since we have everything except for that angular displacement. But I'm going to go with this guy because it's already kind of set up for us, and plus it's also just using all the stuff that was given to us in the question, which just in case we messed up on that last equation, that last thing. Okay, so that's our initial velocity times time is equal to 1/2, not at squared, but alpha t squared. Okay, and then we can plug in our numbers. And what do we get there? We get 6.6 radians. Okay, and that is your angular displacement, which means how many turns did it make? Well, remember, one full turn is 2 pi, which is 6.28. So this is a little bit over a turn, right? Not a bunch over, but like just a little bit. So it'd be like, I don't know, 370 or 80 or something in there degrees. But you can calculate that on your own if you're really, really wondering. But before we do that, I'm going to do one more example. I know, but hey, this is how we get to know this stuff, right? It's just by doing a ton of examples. So, on a game show, contestants spin the wheel. Come on, this is Wheel of Fortune. We all know it. But anyways, the one contestant gives the wheel an initial angular speed of 3.40 radians per second. It then rotates through 1.25 revolutions and comes to rest on bankrupt. Wah, 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 wah. I don't know what sound it makes, but I know it's not just a wah wah. But anyways, bankrupt. Bummer. So we're going to do a bunch of math on this because what else are you going to do? Bankrupt now. So it's the time to do math. So we want to find the wheel's angular acceleration and how long it takes the wheel to come to rest. First thing I want to talk about though, so what do we have? We have the initial angular speed, which is really good. Okay. So we have omega I is 3.40 radians per second. And we want to know how long it takes to come to rest. So we know its final angular velocity is probably going to be 0 radians per second. But it looks like we don't have anything else except for we have this 1.25 revolutions. So we need to use that because that's still telling us something. But it's not telling us in the way that we want it to. So that can still help us figure out what our angular displacement is. Because remember, 1 revolution is equal to 2 pi radians. So if I want 1.25 revolutions, guess what I have to do to 2 pi? I need to take 2 pi and multiply it by 1.25. And that'll get me how many radians I have. That's about equal to 7.85 radians, but remember, do not don't round there, okay? So keep that on your calculator, or just when you need to figure out or use your angular displacement, then just do 2 pi times 1.25 instead. Okay, but there we go. We have our theta as well, our angular displacement. So that's going to make finding the wheel's angular acceleration and how long it takes for the wheel to come to rest is going to make our lives way, way easier there. Okay, so how are we going to do this? Let's figure this out. So find the wheel's angular acceleration. So I have initial, final, and angular displacement. So if I look at these guys, then I'm going to look at what I can use. I'll highlight this in orange this time, I guess, or maybe let's do green. So I don't have time, so I can't use this one or this one or this one, but I can use this one. There we go. That's what I'm going to do because my final angular velocity is 0. So there we go. So for part A, we can use this guy. All right, and then of course we're looking for angular acceleration, so I'm going to rearrange for alpha. So that's 0 radians per second squared minus, what was the initial? 3.4. And then of course that was 7.85 radians. But remember to use the full value, okay? And so if we do that, we get an angular velocity of negative 0.736 radians per second squared. A negative makes total sense, right? Because we know this guy is slowing down. Great. All right, and then part B says how long does it take for the wheel to come to rest? So basically we can use any of the other equations because we're looking for time now. But again, I like to try and not use one. If it's ever possible, I like to try and not use one that uses what I just found or what I just calculated, just in case I did something wrong. So this one, we can still just use everything that we were given in the equation. But again, you don't have to use that whatsoever. You can really, at this point, use any of them. So I'm going to use this guy. And then I'm going to rearrange for time, which will look a little something like this. So that is 2 times 7.85 radians divided by 0 plus 3.4. And that gets us a total time of 4.62 seconds. Okay, and that's it. So, yeah, I know. It's a lot of work and it's a lot to wrap your mind around. So, yeah, just keep going over everything. You'll get it. Do lots of stuff.